Let us consider another diode rectifier circuit. Here the power electronic converter has a diode and a capacitor as shown. The source is of course again a AC sinusoidal voltage source and the load is a resistor R. VO is the output voltage which is defined across the resistor. Consider the positive half cycle of source voltage Vs. So for 0 less than omega t less than pi, Vs is greater than 0, and let us assume that D1 is off when the source voltage is positive. Since we have assumed that the D1 is off, we need to ensure that the voltage across D1 is less than 0, because a diode can block only negative voltage. And when we assume that the diode is off, obviously the current ID1 is equal to 0. So if we need to look at the VD1, voltage VD1, we need to apply KVL in this particular loop. And if you apply KVL in that loop, what you get? VD1 is equal to Vs minus VO or Vs minus Vc. The voltage across the capacitor is same as the output voltage or the voltage across resistor. So unless we know Vc, we cannot say anything about VD1. We know Vs is positive, but we don't know what Vc is. If Vs is greater than Vc, then the voltage across the diode is positive. If Vs is less than Vc, VD1 is less than 0. That means our assumption of D1 off will be true. But as soon as Vs becomes greater than Vc, because Vs is increasing in this interval, as soon as it becomes greater than Vc, our assumption of D1 being off is no longer valid because VD1 becomes positive. Let us assume that D1 turns on at an angle delta from the positive zero crossing of Vs. We will know how to estimate this delta shortly. And when D1 turns on, what is output voltage? VO is equal to the capacitor voltage, which is equal to the source voltage. VO is equal to Vc is equal to Vs, because the voltage across the diode is negligible. VD1 is almost 0. And how does the source current look like? Is is equal to the same as the diode current. ID1 is IC plus IO. And what is IC? IC is C dV by dt, C dVc by dt. That is nothing but C dVs by dt, because Vc is same as Vs. And plus IO, IO is nothing but VO by R, or it is Vc by R, which is same as Vs by R. So the source current is sum of capacitor current plus resistor current. The capacitor current is C dVs by dt and the resistor current is Vs by R. And we know Vs is equal to Vm sin omega t. So we can express the source current as omega c Vm cos omega t plus Vm by R sin omega t. So based on this expression, we can say that the current Is or ID1 starts falling from a peak value ISP as soon as the diode starts conducting, and it goes on for some time. And how long does the diode conduct? D1 is on as long as ID1 is greater than 0, because the current had started falling earlier. So as soon as the current reaches 0, the diode should stop conducting, because the current cannot be negative any further. And let us assume that diode turn off happens at omega t is equal to pi by 2 plus gamma. It actually happens just after the peak of input voltage. The peak of input voltage occurs at pi by 2. So let us assume that it happens at pi by 2 plus gamma. So how do we get the value of gamma? Gamma can be found by equating this equation ID1 to 0. That means 0 is equal to minus omega c Vm sin gamma, because it is cos pi by 2 plus gamma, plus Vm by R cos gamma. That will result in tan gamma is equal to 1 by omega RC. So the diode turns off at pi by 2 plus gamma, and gamma can be found by this expression. What happens after the diode turns off? Once the diode is off, how does the output voltage look like? The output voltage is now solution of this differential equation. C dVo by dt is equal to minus Vo by R, because the circuit is just an RC and the source is simply disconnected. So Vo is the voltage across a resistor. It will simply fall exponentially, and the exponential fall is expressed by this equation. Vo is equal to V1 times e power minus t1 by RC, because we need to write t minus t1 because the fall is starting after a time t1 from t equal to 0. And what is the value of V1? V1 is the value of the voltage at the start of the exponential fall interval. And what is that? That is the point on a sine wave. And what is that value? V1 is equal to Vm sine pi by 2 plus gamma. So from Vm sine pi by 2 plus gamma, the voltage starts falling exponentially as shown here. And how long does the exponential fall continue? It continues as long as this Vc, voltage across capacitor, is more than the input source voltage. So it goes on for the whole negative half cycle, and it may also go on for a short interval in the positive half cycle. And when the exponential fall hits a voltage which is equal to 1 point on the sine wave, the diode starts conducting, and that is what we termed as delta earlier. So we started with the delta because this is the analysis under periodic steady state. We started with a point on any periodic waveform. We reach the same point after one time period. So the diode turns on again at 2 pi plus delta, and the process continues. How can we calculate the time instant of diode turning on? We can calculate that instant by equating this exponential fall to a sinusoidal function. So Vs is equal to Vc at omega t is equal to 2 pi plus delta, and Vm sine 2 pi plus delta is equal to V1 e power minus omega t minus omega t1 by omega rc, where omega t is equal to 2 pi plus delta. We know that V1 is equal to Vm sine pi by 2 plus gamma, and 1 by omega rc can be written as tan gamma as discussed earlier. So we can arrive at this relation: sine delta is equal to cos gamma multiplied by e power minus 3 pi by 2 plus gamma minus delta times tan gamma. We can solve this equation iteratively to get the value of delta, and that gives us the instant, the time instant at which diode turns on. Once we know delta and gamma, we can calculate the average output voltage. And how do you calculate that? Vo average is equal to 1 by 2 pi integral delta to 2 plus delta Vo d omega t, and this integral can be split into two parts because the function has sinusoidal variation in one interval and exponential variation in the second interval. So from delta to pi by 2 plus gamma, output voltage is Vm sin omega t d omega t, and from pi by 2 plus gamma to 2 pi plus delta, it is an exponential function as discussed earlier. So the average output voltage can be expressed in terms of gamma and delta as is Vm by 2 pi into sin gamma plus cos delta plus cos gamma minus sin delta by tan gamma, and gamma is greater than 0 and gamma can be pi by 2 at maximum, because once gamma becomes pi by 2, that means we have already reached 0. The voltage cannot fall any lower. And what is the minimum value of output voltage? Vo minimum is Vm sin delta, and the maximum value of output voltage is obviously the maximum value of input AC voltage Vm. And how about the peak current through the diode or through source? So that can be found by inserting omega t is equal to delta in the first equation for current that we have written. It's basically the KCL equation. So ID1 is equal to omega C Vm cos omega t plus Vm by R sin omega t when D1 is on, and this function has a maximum value at omega t is equal to delta. As omega t increases, this function, the value of this function decreases. So the very first instant of time at which this expression is valid will itself have the maximum value. So that value we are designating as ISP, and ISP is equal to omega C Vm cos delta plus Vm by R sin delta. If you look at the capacitor current alone, that is that omega C Vm cos omega t, that alone in the first interval, and then in the second interval it will be again an exponential function, we can observe the principles of periodic steady state. And how does a capacitor behave in periodic steady state? Charge is balanced, or amp seconds are balanced in a capacitor. There is no net charge that is getting deposited in a capacitor. So the average current through the capacitor is 0. So area A1 is equal to area A2. Area A2 is under this long exponential interval, and area A1 is short interval of diode being on. So naturally, this whole charge that gets extracted from the capacitor in a longer interval A2 should be replenished in a very short interval that spans this area A1, and therefore this ISP, peak value, must be a very large value of current. So to summarize, we have calculated the instant at which the diode turns off in this circuit. That can be obtained by tan gamma is equal to 1 by omega RC. And what is omega? Omega is nothing but the angular frequency of the input AC source, and if 50 Hz is the source, F is equal to 50 Hz, then omega is 2 pi into 50. Then we can obtain delta value by solving the second equation iteratively, and then once we know gamma and delta, we can calculate the average output voltage VO average by the third expression. And what is the minimum value of output voltage? It is Vm sin delta. And if you approximate both the sinusoidal part and the exponential part of the output voltage as straight lines, we can simply calculate the average voltage, output voltage, as Vm plus Vn by 2. That can be one very quick approximate way of telling what is the average output voltage. And the peak of source current is given by Vm by R sin delta plus omega C Vm cos delta using this last expression. What happens when the C value becomes larger and larger? You put larger and larger capacitance at the output side, then the value of omega RC will also be very large. Omega itself is 100 pi for a 50 Hz voltage source. So gamma becomes very small, the interval gamma becomes very small. But of course the delta also becomes larger. Why does delta becomes larger? Because as C is increased with the same value of R, the time constant RC has increased. So the exponential fall will take a longer time to reach the same minimum value. That means in a given interval of time, the voltage to which VO falls will be lesser with higher capacitance, or Vn will have a larger value. So the C value is tripled in one example considered here. So the Vn value increases, so the peak to peak ripple in output voltage, reduces with increase in the value of C. But what is the disadvantage that we get? As the value of C increases, gamma decreases, but delta increases. That means that time for which diode is conducting will be very short. And what does it mean? The charge that is extracted over this interval, the off interval, has to be replenished in a much shorter time. That means the current, peak of the current, has to be much larger, and that is what is seen here. In fact, in reality, this peak value of current can be many times larger than Vm by R. So by increasing the value of C, we may be able to smoothen the output voltage, but we end up drawing very large peaks of current on the input side from the source, AC source.